Purdue University, and he's going to talk to us about how to, instead of trying to verify neural networks after the fact, how to actually build neural networks and train neural networks that are provably correct.
So, good afternoon, everyone. Sorry, so this one doesn't work. Okay. Good afternoon, everyone. My name is Shenkang Lin. I'm going to present our current work called ART, Abstraction, Refinement, Guided Training for Provably Correct Neural Networks. So, as many of us may have known, neural networks have proved to be very effective in many areas, like images, like natural languages, control systems, and many others. In the same time, they are also been shown to be very fragile to be broken, and also quite uninterpretable sometimes. As someone from the PL community, I would definitely hope that these sophisticated models would exhibit some kind of safety properties that will help us better reason about it. Oh, sorry. Like some kind of property saying when the input satisfies some predicates, the output should satisfy some predicates as well. That stimulates our first research question here. Can we enforce a neural network to satisfy some broader class of property phi? In existing works, people have shown that it is possible to show that a trained neural network can be ensured to satisfy phi. However, that is only for backward reasoning. Like, given a trained network and also some formula, you may encode them to a query, to a formula and query some external solver. The solver may return to you, okay, yes, this is that, this is safe. Or it may tell you that it's unsafe, and it will return to you some counterexample. So can we use these counterexamples to enforce the safety property? Unfortunately, that may not be the case. One thing is that it may be endless to always keep querying the solver, and the solver will tell you more counterexamples, but you just don't know how many of them are necessary. And also, these counterexamples are usually few in numbers, comparing to thousands or hundreds of thousands of training data in a training set. So let's revise our motivating question here. Can we enforce the neural network to satisfy phi in a more principled way, like if correct by construction? Luckily, the answer is yes. With the help of abstract interpretation, it is feasible to do this. Here it is the diagram of a typical supervised learning scenario. Well, we add something more to it. We add an abstract domain, and we can also represent the safety properties input predicates and represent them as some kind of input abstractions. These input abstractions are the abstract elements, and with the proper definition of the abstract domain, they can be propagated layer by layer, and eventually we have these over-approximated outputs. For the output predicate, we can define properly some loss function. And the key thing here is that this loss function should satisfy the constraint that if the loss is smaller or equal to 0, then it will imply that this output predicate is proved to be correct. With all these, we sort of characterize a termination criterion for the entire training purpose. So if we know that the over-approximated output has all its correctness loss to be 0, we can be certain that this network has been trained to be safe. So is the question an end? No, because we do care about accuracy as well. After all, who would like any kind of neural network that is absolutely safe, but just outputs you some naive prediction every time? It's safe, but it's meaningless. And for this one, the thing we're just talking about does not suffice. Because if it is just one abstraction, it may be too imprecise. Here's one concrete example. So say the input vector, the input features, there are two features, like the speed and direction, and there are some ranges according to it, and the output predicate says the output category 1, y1, should be always greater than y2. It is interesting to observe that if we just divide along every dimension by bisecting, then the average of the loss will decrease greatly by 23%. And the maximum of the loss for after aggregating all the refined regions will decrease by 48%. And if we just do it more and more, if we divide into 10 equal pieces along every direction, every dimension, the maximum of the loss will be decreasing by an extreme number of 83%. So these numbers tell us that the original loss, the original correctness loss when we're just using one coarse universal approximation is very imprecise. And that is due to that, that's due to the introduced spurious counterexamples from the approximation. So how can, now that's, we need to revise our motivating question again. Can we enforce a neural network to satisfy the safety property phi by construction while penalizing as little accuracy as possible? So to do this, we apply a abstraction refinement mechanism that takes the gradient information from the phi, from the exact same loss that is used to deem correctness for the entire safety property. With this one, we can heuristically decide which specific dimensions are more amenable to decrease the correctness loss. With that, we managed to show that we can answer this specific research question. Moreover, we can show that we both enforce the neural network to satisfy by construction improves the accuracy. That is possibly due to that these very all the accuracy and also the correctness property of the map. That concludes my work. I'm also having a poster there, so you can come to me after, if you have any specific questions afterwards. And I'm also happy to take any questions here. Thank you.
Any questions? Okay, so how big a network can you handle with the abstract interpretation? There's probably like a limit to how big a network you can handle.
So far, the ACAS dataset is not is taking some network of like size of I think it's about the 1,000 neurons around this range, and all these are depending on actually more depending on the abstract domains of the ability to handle the over approximation. So we argue that our approach is more like a model agnostic one. So with the advances of our approach will also be able to handle more and more powerful neural networks as well.
But you don't know, there's no limits, you think?
I think there is some limits there. It's just like with more and more layers, the over approximation and also its introduced spurious counterexamples will accumulate more and more, which may not be directly mitigated just using the refinement algorithm mechanism we're using here. But I'm unable to characterize a specific bound or limit on how much it can handle at this moment.
Verify. Do you also have a limit on the size of the property?
For that one, I don't think there is a size of a limit on the property size. Because all of those properties, especially they can, as long as they can be represented and translated into the loss function I've been describing, and we can show that the loss is decreasing to 0, then it's safe. It is done. There is no limit on what kind of properties and how large it is to handle that.